Right. Good morning, everybody, and welcome to this week's GS seminar. So this week, we're very happy to have Rudolf Zeidler from the Mathematical Institute at University of Münster, and who is going to talk about this extremely interesting topic, positive scalar curvature with point singularities. So Rudolf, welcome, and please take it over.
Yeah, okay. So thanks a lot for introducing me. Thanks a lot for having me speak here. So let me start with my talk. So we'll talk about scalar curvature, positive scalar curvature. Maybe let me just start with a brief introduction of the classical background. So in the end, it will be about singular metrics, but let's start off with just a classical situation of smooth manifolds, smooth closed manifolds, and the question of positive scalar curvature. And the sort of main the main topic will be about closed manifolds which do not support metrics of positive scalar curvature. So I'll mention examples and the relevance of this in a second, but let me just put this down here. So let's start with a closed smooth manifold of dimension at least 3, and such that there exists no positive scalar curvature metric on M. So and here for now this will mean a smooth Riemannian metric G of such that scalar curvature, which I'll denote by scal, is positive everywhere on M. And so there are manifolds which do not have such a thing. And the maybe most classical example that I should mention here, especially in the relativity seminar, would be M, let's say, equal to the torus, or let's say more generally, the torus connected with some other arbitrary closed manifold of the same dimension. So the fact that it doesn't admit positive scalar curvature goes back to Schoen and Yao. And in a sense, I think at least for my suspicion would be for this audience, this will be the most common type of manifold where you're considering for this scalar curvature problem simply because the fact that this doesn't admit positive scalar curvature can be shown to imply the classical Riemannian positive mass theorem. So this is sort of very closely related to the positive mass theorem by compactifying the asymptotically flat end to a torus, and then you can study this by studying closed manifolds and scalar curvature properties on closed manifolds. But for me, actually, I will only be interested for now in this existence problem of positive scalar curvature. Now there are other examples which are, in a sense, which also don't have positive scalar curvature, but which are in many ways quite different. And actually, the main results that I'm going to present will sort of show in what sense they're going to be different. So these are spin manifolds where the A hat genus, a certain topological invariant, is non-zero. So this goes back to Liknerovich. In essence, it's actually older than the torus question, using different methods. And sort of a concrete example here would be the K3 surface in dimension 4. And one sort of very big difference here is that these manifolds here, they can be, so for instance, the K3 surface is simply connected. And there are also other examples here in that class where the hat genus doesn't vanish. So they can be simply connected. Whereas here, of course, in that example, you always have a fundamental group coming from the torus, and they're also related manifolds, which are maybe slightly more general than this, but they also will have always a very non-trivial fundamental group if you're sort of in this Schoen and Yau regime. Now, maybe a third class, which is sort of related, quite similar to the second class, are also spin manifolds, where a different kind of invariant, namely Hitchin's alpha invariant. So this here is this invariant is just an integer, and the alpha invariant is an integer mod 2. So it's a mod 2 invariant. So this here exists in dimensions which are multiple of 4, and this exists in dimensions which are of the form 8k plus 1 or 2. So 1 or 2 modulo 8. So this is Hitchin. And whenever that invariant is non-zero, you also don't have positive scalar curvature. And what's in the concrete examples of this? So a concrete example of this are certain, that means not all, but certain exotic spheres. So this means that you have a manifold which is smooth manifold, which is homeomorphic to the sphere, but not diffeomorphic to the sphere. And certain examples of those in, for instance, first ones that are in that class that I mentioned here would be in dimension 9 or dimension 10. Some of these have such a non-vanishing invariant, and therefore they don't have positive scalar curvature. So this is in a sense quite remarkable that somehow for certain examples, the question whether manifold admits positive scalar curvature or not depends on the differentiable structure. And it even happens in the case of exotic spheres, which of course are very positively curved in the classical case, but these manifolds which are homeomorphic but not diffeomorphic in that case cannot have a positive, not even a positive scalar curvature metric. Okay, so that's the sort of classical setup of the types of manifolds that I want to look at or want to study. Are there any questions so far at this point? Otherwise, I would move on. All right, so let me maybe now come to the sort of main question. Or maybe let's say before coming to the main question, let me also add a remark, namely here the question is about, does there exist a positive scalar curvature metric or not? And you can also sort of ask the borderline question. Suppose there is no positive scalar curvature metric, what happens to non-negative scalar curvature? And that's also has in a sense a classical answer, which goes back to Bourguignon a long time ago. Nowadays, you would probably attack this using Ricci flow, which just says that in this case, so we are always in this regime that M does not admit positive scalar curvature. In this case, if we have the borderline situation, so the scalar curvature is non-negative on M, then the situation has to be very special. Then the manifold has to be Ricci flat. So the Ricci curvature is 0. Okay. And now the question that I want to study is, this is all about smooth Riemannian metrics. We keep the smooth manifold as a background, but we want to relax the regularity of the metric and ask if the same kind of phenomena that I've shown you here, they sort of persist if we relax the regularity of the metric in some sense. So the main theme are Riemannian manifolds, but so smooth manifolds with metric singularities, with Riemannian metrics which have singularities. And what kind of singularities do we allow? So at first we are actually doing something quite general. So we are allowing so-called L-infinity metrics. So L-infinity means here that, let's say in a chart, the metric tensor is L-infinity, but actually what you actually have to make sure is that both the metric and its inverse is an L-infinity. Yeah? And you can express that efficiently just by saying there exists smooth metrics, let's say G0 and G1, such that the metric you're looking at is sandwiched in between this. And this object here, so G0 and G1 is smooth, and this is just a measurable tensor of the appropriate type. Yeah? Okay, so above and below it's bounded by something controlled, but it could sort of wiggle arbitrarily. Of course, that's a little bit too much in general, as you can imagine. So you want to make the you want to add some control, and you can imagine different kinds of control. So maybe you want the metric to be continuous, or you want to have some sort of Sobolev norm to be bounded. What we're going to look at here is something slightly different. We're going to just say that the bound, we don't impose any sort of analytic kind of regularities, but we're just going to say that it's going to be smooth outside a certain singular set, which is supposed to be sufficiently small. So, sufficiently small will usually mean that the codimension of this subset is sufficiently big. And then actually, so the question will be in the end about codimension at least 3. But you can sort of vary a little bit what you want here. And then in that situation, we're going to study lower bounds of the scalar curvature just by imposing the lower bound on the smooth part and not saying anything about the singular part so far. And then the question is, okay, does positive scalar curvature in that sense for a metric which is smooth outside of a sufficiently small singular set, but only L-infinity globally and with a positive lower bound on the scalar curvature on the smooth part, does this impose certain restrictions on the underlying manifold? And there is actually some good evidence that this might be the case. So in the 3-dimensional setting, there is a theorem due to Mantulidis and Lee from a couple of years ago, 2018, 2019, which says that essentially in the 3-dimensional setting, there is no difference between smooth PSC, the existence of smooth positive scalar curvature and having a positive scalar curvature of L-infinity metrics with point singularities. Yeah, so concretely, the theorem says that you have a closed 3-manifold which admits no smooth PSC metric. So here, maybe when I'm writing this, I always mean smooth, and then the question is, can you relax it? Yeah? No smooth PSC metric, and you take any finite subset, and you take a metric of this kind here. Yeah, so L-infinity, this is just what I mean here, and smooth out in the complement of this finite set of points. And you impose non-negative scalar curvature on the smooth part. And then the conclusion is that G is actually flat. Yeah, you have no positive scalar curvature, and you cannot have positive scalar curvature, and you cannot even have non-negative scalar curvature without being flat. Okay, so this is kind of the type of theorem that I want to look at. And now, starting from that, you can, of course, imagine that you might hope that this generalizes into, let's say, arbitrary dimensions or arbitrary manifolds, which do not support positive scalar curvature. And then you should not be able to have positive scalar curvature for these kinds of singular metrics, provided that the codimension of the subset is sufficiently big. And sort of in this paper of Mantulidis and Lee, they also stated this as a conjecture, which they attributed to Rick Schoen, that this would precisely happen for subsets of codimension at least 3. So let me state this sort of as a conjecture here. So you have start again with a closed smooth manifold, which admits no smooth positive scalar curvature metric. And then you take a submanifold of codimension at least 3. And then there are sort of a bunch of predictions. So I sort of this was formulated in a sort of a more compact way, but I separated these predictions into separate statements, so we can look at them individually. So the first, maybe the first one would be there exists no positive scalar curvature metric which is L infinity and smooth on the complement of this codimension 3 submanifold. Yeah, this is sort of the obstruction statement, that the obstruction to positive scalar curvature, which you have for smooth metrics, persists to the singular setting. Okay, that's the first prediction. Then once you have that, you can sort of go to a to the rigidity case a la Bourguignon, saying that, okay, if you have non-negative scalar curvature in this sense, then you actually must be rigid flat. This is sort of the rigidity case. And maybe the boldest question would be to say, okay, in this rigidity case, you actually extend smoothly to all of n. Okay, and in this result of Mantolidis and Lee, so here it was already essentially shown that this implication holds as in the classical case, that whenever you are able to prove the obstruction statement, you will be able to prove the rigidity statement. And they also said that in that case, G extends smoothly to n. So that is sort of in this three-dimensional setting. That's not something that's automatic in general, but at least that holds in the three-dimensional setting. Although also there are some, I will have to comment on this in a second, but let's leave it for now. So just to recap, what is sort of open in general, or what has to be discussed, is whether the obstruction statement holds. If you have that, you will get the rigidity statement, and this is something you have to look at separately. Okay, so what do we know at the moment? Well, let's say up to some time ago. So what are some of the most important known cases? So again, the three-dimensional case is Mantolidis. Then a little bit later, so this was actually published quite recently, but somehow the paper was out for quite a while. Also, the four-dimensional case has been known in quite not in full generality, and it's still not known in full generality, but in quite some generality, in particular in these cases that correspond to the torus and related manifolds. This was shown by Dimitri Katsaros, so the obstruction and therefore also the rigidity statement. And in our paper that I'm going to talk about together with Simone Cecchini and Georg Frenck, we also showed the enlargeable and spin case, which in particular includes this torus case in the spin setting. So assuming that everything is spin here, and finite sets of points. We have the obstruction and rigidity statement, and very recently in a paper of Dai, Wang, and Wei, also the extension part holds in this setting of the torus connected sum of something and finite sets of points. Actually, I'm not giving the full generality here, so they have more results for slightly bigger subsets, but in particular for the finite sets of points, we have that essentially established in full generality for the torus now. Okay, and let me also mention, without giving the precise details, that there are more related results of this kind due to Wang and Xi, and Shi, Wang, Wu, and Zhu from the last few months, half a year or something like that. Okay, so these are sort of the known positive cases. And as we can see, somehow these known cases, they all are sort of related to the torus, or this sort of Shen-Yao kind of setting of positive scalar curvature obstructions. Now let me come to the other case. So the simply connected examples, the K3 surface of Oh, actually, about that I can't say much, but about examples of that kind. And if we in particular look at this last, let me scroll up here, at this last class of examples, these exotic spheres, here there is a there arises a problem. Yeah, and this is sort of the I guess the most explicit problem that I can describe. That's why I'm going to start with this. And for that, let me remind you of the Alexander trick. So the Alexander trick is, let's say, one of the ways of constructing exotic spheres. Well, actually, what it does is that it allows you to extend homeomorphisms from the sphere to the interior of the disk which the sphere bounds. And so let me mention, you start with any diffeomorphism. So actually, for this, you could start with a homeomorphism, but let's just, for later purposes, already start with a diffeomorphism of the sphere of some dimension. And then you can just extend this to a homeomorphism of the disk on the interior just by essentially by coning or by radially extending. In formulas, you can just write it like this. Now you just project the vector to the corresponding point on the sphere, and you rescale it by the length. And of course, this is not well defined, so this would not be well defined at the origin. But here, of course, this goes to 0. So this is also well defined at the origin, maps the origin to the origin. It just cones off the diffeomorphism. And so what type of object is this? So this can be easily seen to be a homeomorphism, but it's in general not a diffeomorphism. It will typically not be a diffeomorphism because at this point here, at the origin, this will not be a differentiable. It will not be smooth there, but it's actually smooth everywhere else. So this is actually kind of nice, except at one point. So it's smooth on the disk minus the origin. And now this kind of trick you can, for instance, use to construct L-infinity metrics with point singularities, just by taking a Riemannian metric, like the standard flat one if you want, but any one actually on the disk, and then you just pull it back with this Alexander diffeomorphism, Alexander homeomorphism. So you can make sense of this metric on the disk minus a point, and it's gonna give you an L-infinity metric on the disk, which is smooth on the complement of the origin. It's just a very simple construction. Nothing happens here actually. And now, one other remark is that if you have one of those exotic spheres, so if you have a manifold which is homeomorphic to the sphere, and let's assume the dimension here is at least 6, then it's always the case that you can write this as a union of two disks, where you glue these two disks along the boundary sphere by a non-trivial diffeomorphism. Yeah, so this is always possible. This is the consequence of the H-cobordism theorem, that you can write any such manifold which is homeomorphic to the sphere as gluing together two disks along a diffeomorphism. And the question of how sort of exotic or how interesting that sphere or that manifold is sort of depends on how interesting in a topological sense this diffeomorphism is. Okay, and now if you have that, you can write down the homeomorphism to the sphere in an explicit way just by using this Alexander map on 1/2. So the standard sphere you can imagine as gluing two disks just along the identity map. And here you have these two disks glued together along the map F. And now you can write down this homeomorphism simply by just saying, okay, on 1/2 we take the identity map, and on the other half we take the Alexander diffeomorphism, then it precisely fits together with the gluing. And now this is going to be a homeomorphism. And Now what you can do is you can also just take any metric on the sphere, for instance, the round metric on the sphere, and you can pull it back along this along this homeomorphism, and it's going to give you an L-infinity metric which is smooth outside of a single point, and it's actually going to be isometric to the round metric in a metric space sense, but you have this singularity because you change the smooth structure on the sphere. And now if you remember that we actually have certain exotic spheres which do not support metrics of positive scalar curvature, we already see that there is a problem of this conjecture. In a sense, a very simple one from that perspective. And I'll just mention this as a theorem. You can just conclude that any exotic sphere admits an L-infinity metric G, which is smooth away from a single point. And there is a homeomorphism to the standard sphere, which is a diffeomorphism outside that single point. And it pulls back the round metric, which I denoted here by G naught, to the metric you have on this exotic sphere. And in particular, this is, in a sense, a very simple counterexample already to the obstruction part of this statement. All right. And now there is sort of the next question I'm going to briefly address is the extension part. So I mentioned that in this case of the torus, we actually know that the conjecture holds. But then if we remember that sort of examples, we also think that there might be an issue, because you can also just do the following. You can start with a torus, and then you take a connected sum with one of those exotic spheres, and then you will actually get an exotic torus. And it can be verified that an exotic torus does not admit a flat metric, and therefore you will see that these exotic tori will admit, just by the same construction, will admit metrics which have singularities, but which are flat outside these point singularities, and therefore cannot extend smoothly. So also the extension part, even in the case where the obstruction part has a slight issue. Now let me just also mention this as a theorem, that if you take any exotic sphere, you can connect it to the standard torus, then you will get something which is homeomorphic to the torus, but not diffeomorphic. This is actually not completely trivial that this always happens. So this for other manifolds than torus, this might not be the case, but for the torus, it is true that connect summing with an exotic sphere will keep it exotic. And you can, using the same Alexander trig construction, just doing it on this part here. Just doing it on this part here will show you the existence of such an L-infinity metric, which is smooth and flat away from a single point. And on the other hand, exotic tori do not admit smooth metrics of non-negative scalar curvature, because we know that if we had a non-negative scalar curvature metric, it would have to be flat. So this is true for any manifold of this form. If you have a non-negative scalar curvature metric, it would have to be flat. But if it's flat, it is not exotic. Therefore, this does not exist. So what to say about this? So this is just to say, I think I just want to make it clear that somehow this problem of the smooth structure has to be addressed in this conjecture, in the sense that we should not look at manifolds which admit no smooth positive scalar curvature metric, but at the very least, we should look at manifolds which are not homeomorphic to manifolds with positive scalar curvature, because otherwise we can do these relatively simple constructions to get a counterexample. And also here, for the extension part, we have to say that this only holds true possibly after changing the smooth structure. Yeah, so in a sense, whether or not you have positive scalar curvature depends on the smooth structure. But once you start allowing singularities, somehow you don't really precisely see the smooth structure anymore. So this is kind of the issue that's going on here. So you have to sort of allow for that. And if you allow that, then this statement becomes true in the case of the torus, and this is precisely the result to die one way. So in their result, they also they will get extension after possibly extending, after possibly adjusting the smooth structure. So then is this part in the case of the torus is okay. So so far so good. And now, are there any questions up to this point, perhaps?
Good. No worries. There's like what's the one technical thing that in the theorem that you stated, that is, if you construct this homeomorphism, but not the the homeomorphism using half the standard homeomorphism with the other half, like this the Alexander homeomorphism. Uh,
Mhm.
so you stated a theorem that that's basically the counterexample, right, of the rigidity statement.
So that's well, that's actually a counterexample to the obstruction statement
Yeah,
already, in a
sorry,
sense.
abstraction statement. No, my bad. Not
Yeah,
rigid, abstraction statement.
yeah,
So,
yeah.
yeah. So what's the main technical thing here? Like in this theorem, like you sketch the sketch the proof. Like you can use this.
Yeah, it's essentially yeah, it's essentially this part here. So that
So this construction of this itself is like very technical. That's the technical part.
yeah, I mean yeah, so that's so well actually yeah, so yeah, that's actually that part, just constructing that that map and then pulling it back. So that's
Okay, I see. Yeah. Okay, thank you.
but let me say, so the so far it's sort of these examples they come sort of out of this subtle thing with the differentiable structure. And might now, as I alluded to, you might want to sort of discuss that in a way and say, okay, these are maybe not the examples I want to look at. I want to look at abstractions which are a bit more robust so that it doesn't depend on a differentiable structure. And here I sort of want to state the main result. We can actually also show that there are examples which are, in a sense, more complicated than that, which don't come out of this relatively simple construction out of the Alexander trick, but which nevertheless still have positive scalar curvature in the singular setting, but not in the smooth setting. So we can show that in any dimension starting from 8, there exists a closed smooth manifold without smooth positive scalar curvature. And maybe let me add as a remark, we can also, so far this would in particular include these exotic spheres, but we can also ensure that these examples don't show up, so that we only have examples which are not homeomorphic to any manifold with positive scalar curvature, so that even if we change the smooth structure, we cannot have positive scalar curvature. So there exists smooth not homeomorphic to a smooth manifold with positive scalar curvature. So the exotic spheres would then not be included anymore. But still, we have a L-infinity metric, which is smooth outside a submanifold of codimension, actually at least 8 in general. If we are now only dimensions which are multiples of 4, we can also just assume that this S is just a single point. In other dimension parities, we have to do some constructions to where the single set will be slightly bigger, but in sort of arbitrarily many dimensions going to infinity, we can also just always have a point, but we have positive scalar curvature on the complement. So this, in a sense, gives more counterexamples. In a sense, from my perspective, actually, in a sense, more convincing counterexamples to the obstruction part, because you cannot sort of discuss them away by removing by changing the smooth structure. And so here, let me just sketch what are the ingredients here. So the first thing is a sort of a topological ingredient, which some people maybe would call that pi principle, whatever that means, going back to so this, in a sense, was first used in work by Grove and Lawson, classifying simply connected manifolds with positive scalar curvature. But then in the way I would need it, it's in another paper by Gaillard, but it's in a sense, this part is quite classical. But what it tells you, if you apply it correctly, is that if you take any simply connected spin manifold of dimension at least 6, then there exists a positive scalar curvature metric on the manifold with a disk removed, which has a collar, meaning that just what I've drawn here. So if you take, let's say, you remove the disk part, and you write down the boundary, the manifold near the boundary as the boundary sphere times an interval, then you can find a smooth positive scalar curvature metric on that part here, which looks like a product near the boundary. So it's given by h plus dt squared in this collar. And what's sort of important here is that h is going to be some metric on the sphere of the one dimension less, so on Sn minus 1. And it has to have positive scalar curvature. So this is a PSC metric on the sphere. But we don't know much about it. So it's going to be, and I think typically it's going to be not going to be in any way related to the round metric. It's going to be sort of a topologically interesting positive scalar curvature metric, which will be quite different from the round metric in the sense that it's not going to be isotopic to the round metric in the space of PSC metrics. So you cannot continuously deform it to the round metric in the space of PSC metrics, typically the kind of metrics that you will get here. But then what you can do is you can build a cone over that metric, and therefore create a singular manifold. Essentially, just by taking that metric here, the one that you get out of the topology, out of the surgery theory, and you cone it off. And then you have to maybe smooth the intermediate part a little bit and adjust the constants and so forth. But you will be able to achieve that it has positive scalar curvature everywhere, well, everywhere where it's smooth, and it has a conical singularity at the tip. That's what you get. And now, essentially, when you combine these two ideas, and sort of the main work is really going to be is sort of in the topology here. If you combine these two things, you get these counterexamples, because now you find these simply connected manifolds which do not support positive scalar curvature because of these spin obstructions that I mentioned in the beginning. And then you can apply this here, and then afterwards you can glue the cone, and you will get a PSC metric with a single conical singularity, even though the original simply connected manifold does not support positive scalar curvature. And concrete examples of this would be, you take K3 surfaces, products of K3 surfaces, and because you need to start in dimension 6, you need to have at least 2 copies of K3 surfaces, and that's why you have to start in dimension 8 here. And actually, you can take any manifold which is simply connected and has a non-trivial A hat genus. And you could also take exotic spheres, but now if we want to if we want to achieve this part here, so this not homeomorphic part here, then these examples are out, and we should not use them. If you don't care about that restriction, you can use them here. And then you can use these constructions 1 and 2 to see that any manifold of that type, namely simply connected and non-trivially heterogeneous, and starting it from dimension 8, is going to be a counterexample to the obstruction part, actually with a single point singularity. Just this conical tip here is going to be the singularity. And then if you want to go from these dimension parities, so multiples of 4s to others, you can just do something like taking a product with an appropriate torus, and you will still be in a regime where you don't have positive scalar curvature, and you will have a small singular set, namely whatever the singular set was, namely the single point times the torus you take. So for other dimensions, you just have to take a product for torus, for instance. And that's how you get these counterexamples, which are not homeomorphic to manifolds with positive scalar curvature. All right, and I think this is something which I sort of changed this a little bit. Now, as a remark, this is what I already said in the statement now, that many of these examples, namely these ones here, and also if you take a torus, they will not be homeomorphic to manifolds admitting a PSC metric. All right, so let me check how much time do I still have?
You still have like 15 minutes.
15 minutes. Okay, so then I can, if then questions at this point, we could discuss them. Otherwise, I would maybe move on to a few additional remarks based on that construction. So maybe let me go up and mention that how can that now we see, okay, so essentially in that settings here, in both of these settings, and I think this is sort of the most interesting case, we will see that the conjecture fails. We saw that the conjecture fails sort of in the most drastic way. Now let me just say how do we actually how can people actually prove the conjecture in that case? How is that done, and what's different? And sort of one thing that's different is that here in that example, we actually know a little bit more. We not only know that M does not admit a smooth PSC metric, we also know that, let's say, I mean, we know many things, but sort of, for instance, M minus a single point does not have a complete PSC metric. Yeah, this for instance, the spin case follows from work of Groff and Lawson, also in the consequence of work of Schulich and Lee, for instance, using mu bubbles. So that's in a sense different from that setting, because precisely the same way as we constructed this cone, we can also get complete PSC metrics on, let's say, the manifold K3 times K3 minus a point. And now the way that for instance, Lee and Mantolidis approached this conjecture was really by taking such an L-infinity metric and doing a certain blow-up construction to make a complete PSC metric on, let's say, M minus the point, or M minus some number of points. And then you apply this complete PSC obstruction. So that's kind of the strategy that you have behind trying to prove the positive parts of these results, or the positive results where you know that the conjecture holds. So that's sort of a very, in a sense, a quite it has a sort of a slightly topological flavor, in a sense that you first, okay, so you do some analytic construction, this or some geometric construction to get a complete PSC metric, and then because the manifold is quite special, it doesn't admit that. You could also imagine a, let's say, more analytic approach to these kind of singularity questions, where you say, okay, you do some sort of smoothing procedure, say using Ritchie's law, something like that, to start from this singular metric, make it smooth, and hope that the positive scalar curvature part would be preserved using the smoothing procedure, and then you could study problems like this, right? Now, these kind of counterexamples that we have here, they of course show that such a smoothing procedure in a sense cannot exist in full generality, because if it would exist for these kinds of L infinity metrics, then this theorem would not be possible, right? Because then you would already get a smooth PSC metric on M, which does not exist. But nevertheless, there are situations, and people have studied this quite a lot, where you can do such local approximations. So you just do some analytic way of approximating the singular metric of a smooth one. There are many results in the Ritchie's law world in particular, and I'll just mention one quite recent one from last year. There are also others by Mansion Lee and co-authors and others, Koch and Lam and Simon, for instance. But I'll mention one due to Paula Burkhardt-Gim, which is just about metrics on Rn. So here we start with some constants and dimensions, and we take an L infinity metric on Rn, which is, however, not arbitrary L infinity. It is close to the Euclidean metric in L infinity up to a universal epsilon, which depends on the dimension parameters. And it's also smooth outside a singular set. And here, what Paula did is imposing a dimension condition, a measure theoretical dimension condition in terms of the Minkowski content. So this is essentially one way, because alpha is at least 2, saying that in a certain sense, the codimension is strictly bigger than 2. And you have non-negative scalar curvature on the smooth part. Then the statement is there exists a family of smooth Riemannian metrics. Let me just say this. So this is smooth, which have non-negative scalar curvature everywhere, and which approximate the given metric in C infinity log on the regular part, as you would expect. And the way this is done is by showing that a suitable version of the Ricci-Turk flow equation can be solved with this singular metric as an initial data. And in particular, this shows that, okay, so you can make the singularities go away here with an approximation procedure. And of course, you can now ask whether you will need this condition here. So this is sort of in a sense, the main difference to what I've been studying before is that this additional condition is here. Of course, it's also an Rn, so you could, but if it's not an Rn, you would kind of imagine that a similar statement should hold on an arbitrary closed manifold. If, let's say, this delta here is going to be some smooth background metric, right? So, but still, okay. So this is an Rn, so you can still ask, okay, do we need that condition? And let me just say the result. So this is a kind of remark here, but the result is yes, you need that. So similar kind of construction, you can construct an L infinity metric on Rn, and so that exists here and in certain dimension pair. It is modulo 8. I think the most interesting one are again 0 and 4, and where you get a metric which is sandwiched in between the Euclidean metric. So it's globally by Lipschitz to the Euclidean metric, but sort of this is not arbitrarily small. So this will be some constant, but it's not going to be arbitrarily small. And it is smoothed on the complement of the origin. So it's everywhere except the origin is smooth, and the scalar curvature is positive. And the scalar curvature actually blows up at the origin, so it can be bounded below by a constant times 1 over r squared. And we can show that we can construct such metrics using such that they cannot be approximated by smooth by a family of smooth metrics with non-negative scalar curvature, which converge to the original G in C infinity lock outside the origin. And the proof idea of this is in a sense similar to the one before. So you take one of these interesting metrics on the sphere, and now you make a global cone over it to get a metric on Rn, which has a single point singularity at the origin. And then you have to do a slightly technical argument, but what you'll essentially see is that if this was possible, if you had such an approximation, you can find a path or a concordance of that metric on the sphere of that H to the round metric. And that you can exclude using topological means from existing for certain H. And then you take these cones over these particular metrics H to get that examples. So that just says, okay, this same kind of phenomenon which prevents this conjecture to hold in full generality also prevents the existence of local approximations of such singular metrics via smooth metrics. As it's possible, as you would have probably expected, given these examples on closed manifolds. So that sort of shows that there is just no local procedure of approximating in that case. And if you ever want to prove a theorem in that generality, like Mantoulidis and Lee, you need to put in some global obstructions, and they just don't hold all the time. All right, and maybe as final remarks, what is actually going wrong? So,
what's the dimension restriction coming from, like in the proof?
So the dimension restriction comes from the question. So you need so this is again a PSC metric on Sn minus 1, which is not concordant to the round metric. So what does concordant mean? So concordant would mean that you want, let's say, a metric H, which is PSC on, let's say, the sphere times an interval 0, 1 with color. So on both ends of this cylinder, it's a color, and let's say H on one end is equal to the round metric, and H on the other end is equal to G. And okay, so you have to show that you have such a metric where this thing doesn't exist, and this can be. I mean, I didn't go into that part for this talk, but this can be done again using index theory, and sort of the obstruction to this only exists in dimension in these dimensions. So this exists basically where you have an A hat genus or you have the alpha invariant, and so it's not. So, in principle, it would be imaginable that you have such metrics also in the other dimension parities, but at the moment we don't have any tools to show that they exist. So that's why this dimension parity restriction is here. Right.
Thank you.
Right. So just the final remark that I wanted to make is that, okay, now so Paula has this theorem. You can approximate locally if you have a if you are sufficiently close to the Euclidean metric, of course, this will fail here. Otherwise, you would have an approximation. Another type of results, which are, for instance, as I mentioned before briefly, to Lam and Simon and Zhu and Li, are under certain Sobolev conditions. And we can actually we could analyze, if you look at these cone examples, they are not just arbitrary L infinity, they also satisfy a certain Sobolev control. So for instance, they are in W2, comma P over 2. So any P is strictly bigger than N, or I mean, maybe that's more interesting is that it's in W1, 1 comma P, strictly below N, this kind of cones. And in particular, this means that the scalar curvature is actually not just, I mean, it's not just defined outside the singular set. You can actually define it as a distribution in actually much more generality. And here it is actually it's a function in L3 over 2, if you want. Now, so in a weak sense, the scalar curvature is defined globally, and nevertheless, you cannot find these approximations. And the reason is that somehow the regularity here is precisely a little bit too low, because there are companion positive results that if you have an L infinity metric in W1 over N, yeah, then you can actually again do this kind of rigidity structural approximations, and you get you get an approximation by smooth non-negative scalar curvature metrics, for instance. So the problem is really that these examples are one of the problems here is these examples are slightly not regular enough, and these examples also show that the boundary here is really sharp of these results here. All right, then let me stop here and thank you for your attention.
Thanks, Rudolf. Thanks for the wonderful talk. So, does anybody have any questions? If anybody have any questions in the audience, please go ahead and mute and ask Rudolf. Okay, I guess nobody has any questions, but yeah, I was wondering, like, in so all of this proof that you've shown is in some way some sort of explicit, like explicit constructions, right? If I'm not mistaken.
Yeah, there's some part which is explicit. So these cones are quite explicit, but these metrics you get, they are not really explicit, right? I mean, they're
Right.
yeah.
Yeah.
So I mean, they depend on doing this Gromov-Loss and Shen-Yao type surgery,
Right.
and so there you would have to decompose your manifold into handles, and I mean, so making that explicit, I think is going to be quite challenging.
Right.
Sort of these metrics you have at the boundary here. I mean,
Right.
once you have them, the rest is sort of explicit. Yeah, that's.
Yeah, this is quite nice. This construction is quite nice, and yeah. Some people actually tend to kind of attend the meeting now. Maybe they have, like, gonna miss the time because the daylight saving. I think is the 1 hour.
Oh, yeah, I guess, yeah. I think I also had to double check because you
Yeah,
switched this week, right? We in Europe, we haven't switched to daylight savings yet. So, but yeah.
maybe I should have, like, mentioned that there are, like, few people actually coming in now, so they must have missed it.
Okay.
Anyway, Rudolph, so a very nice talk actually. Yeah, I'll this is very interesting, and I will,